Hello and welcome to NHP's webinar on safety input devices and applications. My name is Daniel Nathanson. I'm a commercial engineer for NHP Electrical Engineering, specialising in automation and integration products and solutions, and also a TUV Rhineland accredited functional safety engineer. This is just one in a series of webinars created to showcase NHP's smart devices, powered by smart distribution and embedding smart safety into operational processes, providing our customers with better visibility into processes, data, and analytics. In this session, we will specifically be looking at present sensing devices, their application, special function, and specific guidelines and rules on how they should be used, and delve into some of the specifics on how some of these devices work. Present sensing devices are used to detect the presence of personnel or other objects around the hazards of a machine, but not necessarily by providing a physical barrier. We do this where we need regular access to parts of a machine where perhaps a physical movable guard may not be practicable, but at the same time need to ensure that the machine cannot perform processes whilst a person may be exposed. Typical applications where present sensing devices are prevalent are around machines which require frequent loading and unloading of product or regular adding of raw materials. Some of the safety functions which present sensing devices are capable of performing include, but aren't necessarily limited to, emergency stopping, interlocking, and prevention of unexpected startup. Whilst we like to talk about the benefits of present sensing devices, it's very important to consider its limitations before we decide to use it everywhere. The most obvious, but often surprisingly overlooked aspect is that they do not provide any physical guarding. This means that it is still possible to reach into the machine or walk into a hazardous area, as there is nothing physically stopping someone from doing it. Nor does it prevent materials from the machine being ejected outwards, creating a hazard for personnel standing nearby. Milling machines and chippers, for example, will eject material during the process, so you need some physical guarding to protect against this. Present sensing also does not prevent non-physical hazards that might otherwise be protected by guarding. Heat, flames, radioactivity, and excessive noise will traverse the protective field offered by the present sensing devices as if it weren't even there, so supplementary guarding is required for these applications too. And of course, because there's no physical barrier, as mentioned, there is nothing stopping you from physically entering the protected area. The present sensing devices will of course detect you, but the time taken to actuate the safety measures of the machine need to be considered. How long will the machine take to stop from when the safety function is actuated? Fortunately, we have standards to assist us. The standards for safety of machinery provide all the necessary guidance for the selection, positioning, configuration, and commissioning of present sensing equipment, or electrosensitive protective equipment, ESPE, as it's defined in the standard. There are two main standards which we consider when it comes to present sensing devices and their use with guarding. Both of these are part of the AS/NZS 4024 series, which are the main standards used in Australia and New Zealand for safety of machinery. Part 2801 is concerned with the positioning of safeguards with respect to the approach speeds of parts of the human body, and describes the methods used to achieve a minimum safe distance for safeguarding. Part 2802 directly addresses equipment used to detect the presence of persons, and it is the main focus for most of our requirements. This standard covers the operating principles and the different forms and types of present sensing equipment and devices. It also covers requirements for design, selection, installation, and inspection and testing, including the various control techniques and their requirements, like stopping performance, blanking, muting, and the like. Both of these standards are, of course, intended to be read in conjunction with the rest of the AS/NZS 4024 series for safety of machinery, which also includes the requirements for risk assessments, safety categories, and performance level, and other guarding and control measures as required. There are also direct text adoptions of their respective international equivalent, which brings them in line with what we should see on machines coming in or destined to be shipped out to the rest of the world. Part 2801 being International Standard ISO 13855, and Part 2802 is Technical Specification IEC TC 62046. The first and probably most common type of presence sensing device is the light curtain. These are photoelectric sensors which consist of two pieces, a transmitter and receiver. The transmitter sends out an array of infrared beams of light which are picked up on the other end by the receiver. If all light beams are detected and accounted for, then the receiver will provide a pair of output signals which can be used by the safety control system. However, if one or more of the beams are not detected, the receiver will then turn off its outputs. It's intended that the loss of one or more of the beams is a result of them being blocked by a person or object, but could also be a result of loss of power, misalignment of the beams, or other interference. We use light curtains in machine safety as an almost invisible guard around the machine or hazard. When installed correctly, it's not possible for someone to access the hazard without breaking the beams. And if the light curtain is breached, the safety control system will react accordingly and bring the machine to a safe state. I must still remind you that they will not physically stop you from breaking the light barrier and entering the hazardous area. They only detect you doing it. Light curtains come in a variety of different sizes, number of beams, and levels of functionality, and there are specific requirements on how they're installed and used. When we go to select a light curtain, we would need to consider the size of the area we want to guard and what body part we're guarding against. They might be used for point of operation control, where the light curtain is right up against the areas where operators will be stationed, or they may be used around the perimeter of a machine, almost like invisible fencing, as I said earlier, where we only need to worry about a person or vehicle moving into the area. As a result of all these different applications, light curtains come in a variety of resolutions, which is only describing the spacings between the beams. Smaller spacings can be used to detect small-sized objects like fingers or hands, whereas large spacings, whilst unable to detect small objects, are used to detect whole persons or vehicles. The resolution we select has a major impact on what we call the intrusion distance, which describes how far into the hazard we can reach without breaking any of the beams of the light curtain. For example, a 30mm resolution will detect your hand, but that 30mm spacing will still allow your whole finger to go through without detection, provided you're able to slide it between the gaps in the beams. Or a full body type 3 or 4 beam resolution, which has very large spacings, may allow you to reach in with your whole arm or leg before being detected. This intrusion distance has a very real impact on how far back you are allowed to install your light curtain. Tighter resolutions will allow you to position them closer to the machine. However, there is a trade-off on how economic this can be. More beams means more light emitting and receiving hardware, so we need to find the right balance of resolution and distance to ensure an appropriate level of safety without breaking the bank. As light curtains are sensitive to light, as the name would imply, we need to make sure that their surroundings don't interfere with their performance. If we have several areas which have light curtains being used in close proximity, we must ensure that there is no crosstalk between transmitter and receiver pairs. For example, the transmitter on one pair could end up shining onto the receiver of another pair. The simplest way to remove this possibility is to alternate the direction of the light curtain pairs so that the transmitters rather are facing and operate in opposite directions. Alternatively, we could use light curtains which are uniquely coded, which is a relatively new functionality. This requires the light curtain encode a special sequence of pulses in its light beam, which is unique to that pair only. This only ensures that another light curtain pair cannot ignore the signals from others. You can also have self-interference with a single light curtain pair if they're installed nearby to reflective surfaces. The beams are not strictly focused laser beams, so they can spread out and reflect off other objects. These reflections have the capability of going around the object you're trying to detect, so may not work correctly as a result. Aside from removing the reflective surfaces or relocating the light curtains, you might try using baffles on the sides of the light curtains, almost like blinkers on a horse, to help remove light sources that aren't directly in front of the receiver. One of the advanced functions of some light curtains is a function called blanking. What this does is effectively ignoring one or more of the light curtain beams, which allow you to have something traverse the light curtain array without setting it off. We normally use this feature to ignore parts of the machine or work pieces which need to go through the light curtain, while safety is still maintained by other measures. There are two types of blanking, fixed and floating. Fixed blanking occurs when one or more of the beams are blanked, but this does not change during the operation. A typical application will be a conveyor which traverses the light curtain, where we still need to monitor the area beneath, and the conveyor does not change height at all during the operation. However, we may have a scenario where the workpiece in the blanked area needs to move around during operation. This is called floating blanking. This allows the blank beams to move with the workpiece as it moves around freely. However, it must restrict itself so that the blank beams are always adjacent to each other and do not exceed a set limit. This ensures that the light curtains do not accidentally blank an object which is not intended. Blanking, however, almost sounds counterintuitive to how a light curtain is meant to operate. We said that if any one or more of the beams are broken, then the light curtain must trip the safety system. This is true. However, we need to have some level of flexibility with our safety systems, as we do not want it to be a hindrance to our process. A hindrance only serves to motivate someone to try and circumvent the safety systems. So we use blanking whilst ensuring that safety is still maintained by other means. Now, because some of the beams are being ignored by the blanking function, we must ensure that any area which would otherwise be guarded by those beams is still guarded by something else. The workpiece itself should always occupy the blanked area, and any additional space either side of it also needs to be guarded. This can be fixed guarding or removable interlock guards. The light curtain must also operate in opposite mode, meaning that if the workpiece or supplementary guarding is removed, then the light curtain will trip the safety system. It can do this because blanking does not necessarily mean the beam in the blanked area does not exist. Rather, the light curtain is still looking for the beam, but must not see it while blanking is enabled. As soon as it does see the beam, however, it knows that something has gone wrong. The workpiece or the guarding has been removed and will trip the safety system. And also, any distances between the guarding or the workpiece and the non-blank beams will affect the intrusion distance, so this needs to be measured and accounted for too. Safety mats are another type of presence sensing device which detects via physical contact. They are a construction of two conductive plates which make electrical contact when stepped on. By feeding each plate through its own safety control circuit, we can detect whether the mat is stepped on or by monitoring the short circuit that occurs between them. Safety mats come in various different shapes and sizes and can be easily joined together to create large monitoring areas. Now, because the mats are effectively simple devices, they do not perform any self-diagnostics like light curtains or other smart safety devices, and are purely electromechanical. Their effectiveness relies on their reliability and fault resistance rather than fault detection. Consequently, they require regular proof testing to ensure that any otherwise undetected deterioration does not affect its safety performance. Ingress of dust, water, and other substances could get in between the plates and prevent them from fully contacting. Likewise, any uneven or irregular surfaces they're mounted to could also affect their performance. You also need to observe the expected frequency of actuation. For frequent activation, you need to make sure that the number and frequency of actuations is within the manufacturer's specification. And for infrequent activation, you may need to perform periodic proof tests to ensure that the safety mat is still functioning correctly and that any faults are detected before the next demand. It is very important that the installation of safety mat does not cause any other hazards. The mat needs to be firmly anchored to the floor to ensure that it does not come loose and move outside the required detection zone, or to prevent misuse by lifting the mat out of the way entirely. The mat should also not cause any tripping hazards due to the thickness of the mat or loose cables lying around. The cables also need to be protected from mechanical damage. Thankfully, there is an all-in-one solution for these requirements. The perimeter trim, which is often overlooked when selecting a parts list for safety mat applications, but is absolutely necessary. The perimeter trim is a solid length of aluminium which hooks onto the outside of the safety mat and anchors it to the floor. This also has a ramped edge to reduce the risk of tripping and has a cable channels underneath to provide protection for the cabling, which, if you're using multiple joint safety mats, gets to be quite cumbersome. Laser scanners are a nicely unique presence sensing device which allows the configurability of a sensing area like safety mats with the non-contact optoelectronic and self-diagnosing capabilities like light curtains. Unlike light curtains which use a transmitter and receiver, a laser scanner is a single device that operates by diffuse laser light. An infrared laser sweeps an area around the scanner and detects objects in its field of view by measuring how much light is reflected back to it. But it can do a lot more with this. By measuring the time taken for the light to reflect back, it can calculate the distance to the object, and combining this with its position in the sweeping cycle, it can determine where in the zone the object is located. So if we're able to detect where an object is rather than just if it's there at all, we can create protection fields of all different shapes and sizes with different roles. For example, we can configure a warning field which can be used to alert someone about to enter a protected zone or to slow the machine down to a safe speed in anticipation. We can also configure the actual safety field within or next to the warning field to trip the safety system proper. This full configurability allows us to utilize laser scanners in a truly massive variety of applications. In full area access, the scanner creates a protection field throughout the inside of a guarded area to ensure that personnel are protected whilst inside the area. It also has a warning field extending outside, which is used to alert personnel if they're about to enter a protected area as to not trip the safety system unnecessarily. In point of operation control, the scanner is mounted vertically and creates a 2D protective field at the loading-unloading point of the machine. This operates in the same way as a light curtain. Because scanners have a very large sensing range, up to 5 meters for the safety field in some models, They can be used to guard very tall, high access areas. This is ideal where light curtains simply cannot reach the required heights without setting up multiple in cascade. And ultimately, one of the most unique functions is in automatically guided vehicles, where they're used for pre-collision detection of people, objects, and other vehicles. With anything, of course, there are some limitations for use and the requirements to install them with these limitations in mind. Laser scanners, of course, can detect a wide arc and in a variety of different zone configurations, shapes, and sizes, so they should be used to their full extent, which covers their entire hazardous area. You must consider that the scanner cannot detect behind objects in its field of view. If there is a large fixed object in the field and is included in the zone mapping, you need to ensure that the area behind the object is not capable of creating a shadow large enough that a person could enter the protected area without detection. You may need to add in supplementary guarding or an additional scanner. Multiple scanners can be used to overlap the same field and detect around objects, which create shadows to other scanners. However, as both scanners are light emitting and receiving devices, you must ensure that they do not interfere with each other. It is often recommended by manufacturers that multiple scanners in the same area are mounted at slightly different angles and heights, such that the 2D plane of their scan fields do not intersect. And similarly to light curtains, ensure that there are no reflective objects or intense light sources nearby which could interfere with the scanner. When using scanners for mobile applications like automatically guided vehicles, it is important to consider that the vehicle does not pose any risk with respect to trapping or crushing hazards at the edge of the detection zone. This means having adequately large detection fields in conjunction with a known stopping time and distance. And as the vehicle travels, ensure that there are minimal changes to the physical environment which may affect the scanning and stopping performance. Things like approaches to reflective surfaces, water, oil, or ice, changes in the incline, uneven surfaces, etc. As I mentioned at the start of the session, presence sensing devices do not provide any physical guarding. You can walk straight through or reach into the machine and there is nothing stopping you. So we need to ponder whether this solution is practical for our application and consider some of the aspects of our machine. For example, the stopping time of the machine could be long. Once we de-energize the machine, how long does it take to slow down to a safe speed? How quickly does the safety equipment involved to perform the safety function, and what's its responsiveness? What is the approach speed? How fast is someone walking, or how fast are their limbs might move into the protected area? And how far could you reach into the protected area before being detected? All of this determines how far back we have to position our presence sensing equipment in order to ensure that if someone traverses the protective zone, the machine has gotten to a safe state by the time they reach it. This is called the minimum safe distance. This sounds like a daunting task, but the good news is we can calculate it, and the formula is provided to us in the standards, namely AS 4024 Part 2801, which is the standard for positioning of safeguards with respect to the approach speeds and parts of the human body. In this standard, we also have predefined values for human movement, speeds, and other characteristics, which we can use to aid in our calculations. The formula is as such: S equals K times T plus C, where S is the minimum safe distance that we want to calculate, and it's given in millimeters. K is the approach speed of the body or limb in millimeters per second. T is the overall stopping time of the machine, given in seconds. And C is the intrusion distance, or how far can we reach into the protective field without tripping anything, again given in millimeters. Let's go back to this machine which we saw earlier and use it as an example on how we calculate the minimum safe distance. The application involves a normal approach towards the machine, which is being guarded by a through-beam light curtain. The light curtain is monitored by a safety monitoring relay, which in turn controls some isolating contactors. The safety function in this case is to de-energize the contactors and isolate the machine when the beams of the light curtain are broken. Consider the normal approach speed as provided in the standards is 1600 millimeters per second, 1.6 meters per second. That's the K in our formula. For the response time of the system, we need to consider all of the components involved and the order in which they respond. We can generally get this data from the manufacturer. In this case, the light curtain takes 13.2 milliseconds from the time the beam is broken to the actuation of its outputs. Next is the safety monitoring relay, which takes 35 milliseconds from detecting the signal from the light curtains to actuation, and the contactors, which take 60 milliseconds to de-energize and open the contacts from when the coil is de-energized. But this isn't all. We need to consider how long it takes for the machine to slow down sufficiently to be safe. We tested this, and it regularly takes no more than 2 seconds. The last factor we need to consider is the intrusion distance, which is how far we can reach between the light curtain beams without being detected. We also get this value from the standards and is given to us as 850 millimeters, considering the type of light curtains, number of beams, etc. We have all our factors, now we're ready to plug it into our formula. We add up all of our t values, which is the total stopping time, and we end up with a minimum safe distance of just over 4.3 meters. Wait, we need to put our light curtains no less than 4.3 meters from the machine? What a waste of space! So would we consider presence sensing practical for our application? Should we maybe be using locked guarding instead? Maybe we don't have to. What if we could change some of the processes and stop our machine a bit quicker, and perhaps use a different type of light curtain with tighter spacing between the beams? Let's work this out again. We have the same approach speed, that hasn't changed. We're using different light curtains though, so from the manufacturer we've ascertained that the response time for these light curtains are 23.8 milliseconds, a bit longer than before, but let's keep working through the exercise. Safety monitoring relay and contactors haven't changed, but we have a shorter stopping time, which we're confident will stop within 200 milliseconds this time. And our intrusion distance will be different now too, because the light curtain beams are spaced much closer together. I can't reach in as far as before. Using the standards again and considering a 30mm beam spacing, we have determined that our C factor is now 128mm. We plug our values back into the formula again. This is a much friendlier number, just under 640mm. We can certainly deal with that, and we don't have to install our light curtains as far back as before. Another advanced function of presence sensing devices, or rather application, is muting. Muting is done to temporarily suspend the safety function of the presence sensing system and is performed automatically. This also seems counterintuitive to the purpose of our presence sensing system. Why on earth would we want to prevent them from detecting something when that's their whole purpose? Just like blanking, muting is done in order to provide flexibility in our safety control system, so it does as little interference with our machine processes and not cause a hindrance, and when done correctly, is perfectly safe to use. We use muting to allow materials to pass through the light curtains without tripping them, but only temporarily. Once the material has passed through the light curtains, we want to resume all normal safety operation of the presence sensing system. We typically see muting performed on conveyors, palletizers, and packaging machines, and usually with light curtains. Muting also needs to be done automatically by the safety control system and should only be enabled during a very specific set of criteria. So in order to enable the muting function, we use a set of specially positioned sensors near the light curtain to detect the materials approaching, and using a safety logic controller to determine whether the muting criteria is satisfied. The logic can be performed either integral to the light curtains or outside using a separate controller such as a safety PLC or a specialized safety monitoring relay. And of course, because we are suspending the safety function of the light curtains or other presence sensing device, there is a whole set of requirements we need to meet to ensure that this is done safely and effectively. Firstly, muting should only be used when it is necessary for the process of the machine. If you don't necessarily need to use muting to perform the safe task, then don't use it. It's very simple. Depending on the risk assessment, you may need to have an indicator which shows when muting is currently active. There isn't a specific color or type of indicator which is designated to the muting function, but it should be selected so that it's sufficiently bright and readily visible from any foreseeable position where a person can attempt to access the hazard, and you should use a color which cannot be mistaken for any other process of the machine. Muting also needs to be initiated and terminated automatically. The conditions which this occurs need to be from appropriately selected sensors or another reliable signal from the safety control system, and incorrect signals, sequences, or timing should not allow muting to occur. Other things to consider before applying the muting function. Initiation and termination should only occur at appropriate times in the operating cycle, so muting cannot be enabled unless there is material that needs to pass through. It needs to be initiated by 2 or more independent muting sensors. One sensor is not enough and can easily be defeated. Use timing or sequential control, preferably both together, to ensure that muting sensors are detecting the correct material. This also helps prevent defeat, but also makes sure that the muting function is not left on unnecessarily. Sensors need to be protected against the mechanical damage and or misalignment. This also includes protection against any unforeseeable manipulation to try and circumvent the safety system, and ensure that there are no trapping or crushing hazards from the materials being transported. Now, this isn't necessarily an exhaustive list, so you should refer to AS 4024 Part 2802 to ensure that you've met all the requirements and considerations for muting. As far as the muting sensors are concerned, there are several different ways that we can use and arrange them, depending on our muting functionality. It's very typical to use photoelectric sensors in muting applications, however, other sensor types may be used depending on the type of material being transported. In this example, the sensors are arranged in a cross pattern, where two sets of beams from the sensors intersect just before the light curtain beams. This is called the T-type arrangement, and is used with both timing and sequence control between muting sensors and the light curtains themselves, ensuring that the material clears the light curtain area before muting is terminated. The positioning of the muting sensors and the beams are specific to the type of material which it's detecting, which limits the likelihood of an unintended activation of the muting function. This arrangement can be used for both entry and exit through the light curtains. Another arrangement with two sensors is the L-type, where both sets of sensors are behind the light curtain in the hazardous zone. The beams are arranged in parallel and are also used with timing and sequence control. This time, the material can only move in one direction through the light curtains. However, as both muting sensors are located behind the detection field of the light curtains, there is minimal risk of the sensors being manipulated, as the light curtain beams need to be broken before accessing. In this arrangement, the muting is terminated as soon as the material leaves the light curtain field. A four-beam arrangement consists of two sensors inside and two sensors outside the light curtain field. This works in the same way as a two-beam L-type, but allows for movement in both directions. This system also relies on the correct sequence and timing of the sensors and light curtains in order to initiate, maintain, and terminate the muting function. The spacing of the beams as well requires that there is at least one muting sensor detecting the material as it passes through and ceases muting once the material has left the light curtain field. We need to be careful with muting so that we're only detecting the material that needs to pass through the light curtains and not anything else. If the sensors pick something up that's moving too slowly or too quickly through the muting sensors, then it is likely that that is not the material that we want. Likely someone is trying to defeat the safety system, or it could even be an empty pallet. This is why it's very important that we understand what our machine is capable of doing. How fast does the material move through normally, and what is the size of the material? The sensors also need to be arranged so that they only detect the material and not anything that is carrying it like a pallet. What we don't want is an empty pallet passing through without anything on it, and the muting sensors allowing it through. This could allow for a fake load, like a person, to go through the light curtains undetected. We also need to ensure that whilst muting is active, that there is no other way that someone could gain access to the hazardous area. The light curtains need to be positioned as close to the material as possible so as to prevent someone from moving through a gap between it and the light curtain or other guarding. If you recall, this was the same requirement for blanking, and that any gap remaining needs to be considered as an area of intrusion, so how far could you reach in, if at all, through that gap? But what happens if you trip the safety system whilst the material is in the middle of passing through it during the muting function? If you try to restart the machine, the muting function is already terminated, so any material stuck between the light curtains is going to be detected and prevent the startup. For this reason, we may require a manual override, something which bypasses the safety system to enable you to jog the conveyor enough to clear the material from the light curtains. However, we need to be very careful how we implement this manual override, because I just said that this was a way to bypass the safety system, something that we usually don't want to happen at all. As such, we have some special requirements for how we implement the manual override to ensure that it cannot be misused or manipulated to circumvent the safety systems. Firstly, the type of operator which is used to activate the override should be a momentary type spring return, for example, such that you have to actively and physically hold down the operator whilst override is in operation. This is so that if you let go of the operator, the override is terminated. The operator also needs to be located in an area where it is not possible to enter the hazardous area protected by the light curtains, but keep the area visible. This is so you can see that the blockage is cleared, but also so that no one is in the area that could be injured. You could also use a key-operated switch or similarly secured operator to ensure that only authorized personnel can activate the override. In any case, the override should only be allowed to activate whilst one muting sensor is actuated, and this is also to prevent an override from being misused to allow entry into the protected area. It should also be automatically terminated after a time limit has expired, and or after the last muting sensor has been cleared. If we look to the circuit on the right, the block responsible for the override function, OVR, is only energized from one of the muting sensors S1 or S2 and the timer. When we activate the switch, the timer energizes but only remains on for the duration of the muting function, which we allow for. After this timer expires, the contact opens and override is terminated. Likewise, when both muting sensors are deactivated, the override function is also terminated, whichever occurs first. The manual override should only enable the necessary movements of the machine in order to clear the blockages. It cannot be used for any other manual operation of the machine, only to clear the blockage and only for the muting function. And as usual, AS 4024 Part 2802 contains all the requirements and even several further examples on how muting and the override function can be achieved properly and safely. And so concludes today's session on presence sensing. By now you should have some more intimate knowledge on the function of the various types of presence sensing devices, their applications, and some of their special requirements. For more information on the selection or even just on machine safety in general, there is a wealth of information available in the NHP Machine Safety Selection Guide. I also highly recommend reading through Rockwell Automation Machinery Safe Book 5, which is a bit more advanced but provides fantastic guidance around designing and navigating machine safety control systems. Thank you for joining us for this webinar. I hope you found it beneficial, and if you'd like to watch it again or to find more webinars in this series, please go to nhp.com.au or our dedicated NHP YouTube channel. If you have any further questions about machine safety products and solutions, please contact your local NHP sales representative. With smarter and faster decision making and seamless connectivity spurring new collaboration, NHP is enabling the connected enterprise.